Hello everyone and welcome to this tutorial on QUIC, Quick UDP Internet Connections. My name is Tejas Noor and this is my submission for SIT 202 Task 6.3 HD. In the next 10 to 12 minutes, I'll quickly walk through QUIC, what is it and how it is created, how it works technically and how it is compared to TCP and UDP, real world applications, security connections and many other things. Finally, we'll go on Wireshark analysis. So let's get started. So in this slide, I'll tell about my agenda. What is my agenda for today? We'll start with the basics, what QUIC is and how it is needed. Then we'll dive into technical details such as handshakes, formats, and how it compares to an existing protocols. We'll look who uses QUIC today, its security, what are its security implications and scalability. So moving on to the next slide, what is QUIC? QUIC stands for Quick UDP Internet Connections. It is modern transport layer protocol that was originally developed by Google in 2012 and later standardized by IETF as RFC 9000 in May 21. Unlike TCP, QUIC runs on top of UDP. This is deliberate design choice. It allows QIC to bypass the limitations backed into TCP while still benefiting from the UDP simple, like it basically means that it uses the TCP model baking into the benefiting of UDP simple process. QUIC has four defining characteristics. First, it runs over UDP. Second, it has built-in TLS 1.3 for encryption. We cannot use QIC without encryption. Third, it achieves very low latency through one RTT or zero RT connection setup that I'll show you when we'll go on the Wireshark. This is the timeline which I have shown here. So the fourth, it supports stream multiplexing. Multiple data streams can flow over a single connection simultaneously without blocking each other. This is a huge benefit. Like we studied about multiplexing, we can relate that. The timeline on the screen shows how QIC evolved from an Google, then public announcement and moving further on. Let's go on to the next slide, which will be on why do we need QUIC? So to understand this, we need to look at the problems of TCP. The first problem is the setup latency. To understand what is latency, it can be basically understood by a simple method like server requesting server something and the delay the server is taking in, the delay the server takes in responding to something. That is latency. So the TCP's three-way handshake combined with a separate TLS negotiation requires 2 to 3 round trips before a single byte of application data can be sent. On a mobile network with 100 ms latency or 200-300 ms is wasted before anything loads. This is only a time wastage which is covered by this QUIC. The second problem is head of line blocking. In TCP, one packet is lost, all the data behind it in is held waiting for that packet to be retransmitted. This is crippling for HTTP version 2 multiplexing, which is supposed to solve this application layer but couldn't fix it at the TCP layer. Third, the TCP has no built-in encryption. TLS layered is separately and as an afterthought. So moving on to the fourth, the TCP suffers from protocol ossifications. That means the middle boxes like firewalls and NATs have been so extensively deployed over decades that they expect TCP to behave in their specific recommendations and ways, making it nearly impossible to evolve the TCP model. TCP model, the TCP way. Finally, TCP connections are tied to an IP address and port pair. Change your network, say for example, switching from Wi-Fi to 4G, and your connection is dropped. QUIC addresses every single of these. It combines the transport and TLS handshake into one RTT. It eliminates head-off blocking by having independent streams. Encryption is mandatory. It runs over UDP by bypassing all the middle boxes, and it uses connection IDs instead of IP ports, enabling seamless network migration. So now I'll go on to the next two slides, that is how QIC works and what is the frame format of it. So let's talk into the QIC, what actually we see in this protocol. Looking at this protocol, the top we have the application, for example, HTTP version 3. Below that, QIC handles both transport and TLS 1.3 version in single integrated layer. QIC is UDP and below is IP. This is fundamentally different from TCP plus TLS model, where transport and encryption are separate layers. QUIC has five functionalities. That is, stream multiplexing allows multiple independent byte streams in one connection. Stream IDs are odd for different initiated, even for server initiated. The one RTT and zero RTT handshake allows first time connections in one round trip, and returning clients can send data with the first packet using cached session tickets. Connection migration uses connection ID rather than IP and port to identify connection. So switching from Wi-Fi to mobile doesn't even break your connection. Credit-based flow connection operates numbers for more precision and detection than TCP's approach. Now we'll move on to the next slide. QUIC uses two header for types. During the handshakes, long header packets are used. They contain a header form fit, a fixed bit which must be one, the packet type, initialized for the first contact, 0 RTT for the connection ID, and payload. After the handshake, shorter packets are used, which are much smaller. The most important QIC frame types are stream for the application data, ACK for acknowledgement, crypto for TLS handshake, connection underscore close to terminate max data. Max data is for flow control, and padding is to meet the minimum size packets required. Moving on to the next slide. So in here I'll explain handshake comparison between TCP and QUIC. This is one of the most important slides of my submission. The handshake compares between TCP TLS model and QUIC. On the left, TCP plus TLS version 1.3 requires two round trips minimum before data flows. First, RTT synchronization SYN, synchronization acknowledgement to establish TCP. Then the TLS client hello server exchange for encryption. That's at least 200 milliseconds on a typical connection before a single byte of your web page starts arriving. That's a lot of time in today's world. On the right, QIC merges both into a single step. The TLS client hello is embedded into the first QUIC initial packet. The server responds everything it needs in one go. Just after round trip, the server responds everything it needs in one go. After the I just wanted to say, after just one trip, application data is already flowing and the return clients. The zero RTT case, QIC uses a cache session ticket to the application data where the absolute first packet before any response from the server. This is a massive improvement in the latency and how we use from switch from mobile networks to 4G, 5G, Wi-Fi to 4G, 5G. So moving on to the next slide, what are the advantages and disadvantages of the QUIC model? So it has faster connections, that is one RTT, zero RTT. On the other hand, we see two other protocols which didn't have this. No head of line blocking cross streams. Encryption always on, cannot be disabled. Seamless connection migration across networks. Congestion control is user space. That means it will be a faster evolution. Better performance on high latency networks. So let's move on to the next slide. Real world application. QUIC is not experimental, it's running in massive scale right now. We can say that Google has deployed QUIC on search, YouTube, Gmail, Chrome since 2013. Over 15% of the connections Google services already use QUIC, and Cloudflare enabled QUIC on its edge servers also. And the Meta deployed QIC in 2018, especially for mobile apps where lossy networks make TCP head offline blocking particularly painful. DNS over QIC is defined as RFC 9250, which encrypts DNS queries for better privacy. Moving on to the next slide upon security threats and mitigations. We can say that, like any other protocol, QUIC has security challenges. Let me walk through one of the main threats, and then we'll move on to the scalability and the Wireshark demo. So first, handshake flooding. Similar to the TCP synchronization flood, attackers send many initial packets to exhaust the server. QIC addresses this with retry packets. The server focuses on the validation step before allocating any state, providing client's IP is real. Second, zero RTT reply attacks. Because zero RTT data is sent before any server responses, an attacker can capture and relay those packets to trigger repeated server actions. Server must be zero RTT as a non-implementable and restrict it is safe. Read-only request. Third, connection ID manipulation. The attackers alters the connection ID fields to hijack or misdirect traffic. QIC cryptographically binds connection ID to encryption keys. Fourth, trafficking fingerprinting. Even with the encryption timing, packet size patterns reveals which sites a user visit. Mitigations include encrypted client hello and padding packets to uniform sizes. Finally, amplification attacks. The server's initial response can be larger than the client's request, letting attackers amplified DOS traffic, quickly strictly limiting the server response to three times the bytes received until the client is verified. Moving on to the next slide about the scalability. There are many factors which make this model very scalable, which is in this, like I'll quickly say that the streams per connection is 2 raised to power 62. Stream data is also 2 raised to power 64 bytes. The connection IDs enable load balancers to route QIC. Even the clients move between the networks, as I have talked about this in my whole video. User space congestion control. Unlike TCP kernel space, it has a very better way of which is very fast evaluating user space congestion control. Multi-patch QIC feature. Drafts especially allow QIC to use multiple paths simultaneously. 4G plus Wi-Fi in the technology we are using today in our phones also there is option of using both simultaneously. Version negotiation. QIC supports protocol version negotiation. New features and improvements can be deployed. Real adoption that we can see that 8.9 of all the website today which are deployed are using QIC HTTP version 3. We can see that in the future it will be a very scalable and it is already scaling. So now I'll show I have captured my Wireshark, how I have analyzed Wireshark and QIC. So we'll move to Wireshark. I have already filtered out the packets for QUIC. So we can see that the initial packet, the 266, will open this and I'll moving on. So this is the uh, client hello inside the crypto packet. So we'll go to the crypto and we can see, yeah, here we can see that it uses the TLS 1.3 and which is this fragment and it is basically a client hello long header format. We can extend the packet and see the connection ID to, I'll show the connection ID. The connection ID is here, source connection ID. So after the handshake, the packet switch between short headers and the smaller overhead. I'll filter out the specific connection ID. I can track the entire session, even the IP address which changed. So we'll see now the padding length. So this is the padding and it has to be at least 1200 bits to reduce amplification attack risk, and it is actually 12. I have totaled the sum and it is above 1200. So this was all of the QIC on Wireshark, and I'll show you the acknowledgement packets too. This is the acknowledgement packets 271. I'll open this and I'll show that, yeah, it's showing the frame type acknowledgement largest. This should be one and it's one. I'll also show how the other packets work. So according to this is the protected payload. We can see that it has the connection IDs of both source and destination. This is the main QIC which shows all the destination source ID and length of the packet. I'll yeah, this I wanted to show that QIC uses short header which I was talking about but couldn't show, and here I show.